Okay, so let's talk about vectors for a hot second. Anybody care to tell me a thing they know about a vector?
It's got direction.
Good, a vector has a direction. Okay, so I'm going to note a vector v like this. So this is a letter v with a little symbol over the top of it. In written communications, that is bold rather than hatted. So be aware that the book just bolds vectors. If I ask you chess questions, they'll be typeset, so they'll be just bolded too. And out of a vector v, we think that it has a direction. And in the chat, I'm seeing also a thought about magnitude. Okay, so this is kind of the Calc 3, the kind of Calc 3 or physics thought about vectors, right? And in an example of a Calc 3 or physics style vector, I might have v is the vector 1, 2. Are you with me on that? Okay, so tell me about the direction and magnitude of the vector 1, 2. What do you got?
Well, the direction is heading infinitely towards the first quadrant, and then we can find the magnitude using Pythagorean theorem or the direction formula or distance formula.
Okay, good. Yeah. So if we wanted to know about the magnitude of this vector, we could use the kind of thought about length that we're going to get to in the next section, which is really just Pythagorean's theorem. Another thought we might have about direction is that this is kind of 1 in the x and 2 in the y. You guys all with me on that? So I might think of this as kind of this picture that's 1 over in the x and 2 up in the y, and here is the vector I'm talking about. Are you following along with me on that? Okay, so that's kind of the Calc 3 style thought. Now, in our linear algebra style thought, we're going to do things a little bit differently, but the same. So that difference is going to be that I'm going to talk about a vector v, and instead of writing it as 1, 2 in some kind of angle brackets, I'm going to write it as 1, 2 in a little box. This is the same thing. It is written differently for reasons. Those reasons will become apparent as we kind of manipulate things a little bit. But for right now, I just want you to know that I changed notation on you and it was unfair and you should resent it. Pretty with that? Yeah. Has everybody seen vectors before in the context of physics or calculus or something? Alexis, I'm looking at you. Am I seeing imperceptible nodding? Okay. So if we've seen, you can unmute and talk. Tell me about it. What's your experience with vectors?
I took physics. I'm taking physics now, and I took the first semester over the summer online. So that's my knowledge of vectors. Okay,
cool. The good news is it doesn't really matter at all, except that I want you to be comfortable with the idea of a vector and hopefully some operations. We're going to treat these a little differently than we do in physics and Calc 3, so don't feel bad if you've missed one of those things. Okay. That said, feel good if you've had that thing, because at least you won't be scared of them right off the bat. Cool? All right. So this is the same thing in a different notation. I think exactly the same picture at this. It's 1 over, it's 2 up, it's this arrow from the origin. So nothing has changed except this notation. Pretty good with that? Okay. So now we have some thoughts that we need to recall. about maybe vector operations. So can anyone tell me the Calc 3 vector operations that I should have been concerned about?
Is it the dot product and cross product for 2?
Okay, so in the physics or Calc 3, I had dot product, I had cross product, I had, what else? Dos más.
Vector addition.
Good, addition, and one more. It's another kind of multiplication.
Scalar multiplication.
Good. Okay, so the things that I'm going to keep for my linear algebra thoughts are, I'm going to talk about addition here. We should talk about scalar multiplication. We're going to talk about dot products in the next section, which we'll probably get to today. And cross products we might never talk about really in the context of this course. Is that true? No, that's maybe not entirely true. We'll probably talk a little bit about cross products. The thing I really need you to remember about cross products is that they really only happen in R3. And so they're just a little bit special. Does that make sense? If you don't remember or know what a cross product is, don't worry about it. If you remember or know what a cross product is, and you don't remember that it's only in R3, be concerned. Okay, so let's talk through vector addition. If I have a vector v and a vector w, and I want to stick them together with addition, what kind of thing does this make?
Vector VW.
Good, this makes a new vector something. Let's call it u. Oops, that's a shitty u. And u is a vector. Pretty good with that? Okay, quick question. Can I add 3-dimensional vectors and 2-dimensional vectors together? Oh, wait, sorry, roll back one. Precursor question. I have given you thus far a what dimensional vector as an example?
2-dimensional.
Good. I gave you only so far a 2-dimensional vector, right? This thing is a 2D vector, i.e. R2 as a vector space. Good. Yeah. So now the question is, what's the difference between a 2D vector and a 3D vector? So if I wanted to make a vector W that was an element of R3 as a vector space, first, have I tripped notation on anybody? You'll know what all the symbols mean.
After you accused, who was it, Joe, of, or no, it was someone else from Calc 3 of writing equals certain conditions, I think I've learned my lesson.
Oh yeah, so the good news, guys, is that while I've had you in a course previously, I have a very short attention span. And so while I remember that I've had you in a class, and I like you because I've had you in a class, I do not remember anything about your performance in that class. You all get a blank slate, even the ones who should get some credit for doing well in the previous course. So no, I won't. I will try to do my best not to call people back. ish, Jackie. Well, I think I only remember that we had to reschedule for some reason. I don't remember why. See, it's good. Okay, so if I want to make a three-dimensional vector, these symbols mean W in R3 vector space. So that would be the space of three-dimensional vectors. So if I want to make a vector W in the space of three-dimensional vectors, what is the distinction between that thing and this V that I have up here? I promise this question isn't as hard as it seems.
It has a third direction / coordinate that we're keeping track of.
Good. Yeah, it has a third component. So if I want to make a vector W, I just say, all right, I just need 3 numbers. Okay, now the kind of more philosophical distinction here is that a 2-dimensional vector represents a force in 2-dimensional space. So this is a push, right? A magnitude in a direction, you can think about it as a push. So this is a push in a plane. Right, so this is, you have a billiard ball and you whack it. Right, that's for the most part at least, is a 2-dimensional force. Now a 3-dimensional force is a magnitude and a direction, but in 3-dimensional space. Right, so this is a force in 3 space. So this is like when you, well, in the billiard ball analogy, right, this would be thinking about whacking a Christmas ornament off a tree with a baseball bat, right? It might go up or down or kind of, you guys all with me on the 3-dimensional nature of that? Okay, so the only difference in this case is really why. I'm sorry, John, I don't know what the question is. Got it. That wasn't a question, that was a statement. So I've got my 2-dimensional forces, I've got my 3-dimensional forces. Past that, I'm probably not going to think about things as a force. That sort of makes sense? That said, keeping track of a 7-dimensional vector is going to make a lot of sense in this class. It's going to be something super easy that we do. Don't make that face at me, Jordan. I know you've written computer programs. What?
I have 0 idea how to program. I have a tough time manipulating GeoGebra because I have 0 programming skills.
Well, damn it, Jordan. I thought you had been in one of the computer classes too. Okay, so let's suspend disbelief for a second and believe that we might have a case for keeping track of more than 3 pieces of information. You all believe that at least? Okay, so linear algebra is going to be in large part about manipulating vectors. Sometimes those vectors are going to represent data, right? And if I think about what it takes to put, oh, I don't know. So I did this yesterday. I signed my grandmother up for a COVID vaccine, right? In that process, I had to submit like 20 or 30 pieces of information about her to a computer system. You guys see that? You guys are used to doing this, right? You sign up for an account for a new chat app or, you know, whatever. Like Discord, right? You had to submit some information to sign up for Discord. How many pieces of information was that? I don't know, maybe 5, 6, maybe even just 2 or 3, right? Depends on the service. Depends on what your user account consists of. How many pieces of information are on your driver's license? Hell, if I know, probably 30, maybe more, right? Some of those I have control over, some of them the state has control over. But if the state decides that they want to do some analysis of the data in their driver's license system, right? Then they're going to be treating all that information that's on my driver's license as a vector. And they're going to do some information like calculate the average BMI of every person in California, right? And the way they're going to do that is they're going to write a formula that takes the height and weight information out of the driver's license, right? And churns on it a little bit. You guys all with that as an idea? Okay, so that's one use. Other uses are things like you as a human being in services like Facebook or Reddit or Netflix or Amazon Video, like all of those, or Spotify, Pandora, all of these services that kind of recommend the next thing for you. You as a customer are represented as a big ass vector of preferences, right? And then what they do is they find things that are close to your vector. That makes sense? So in some sense here, we're going to think about vectors in 4 space or 5 space in this case. And you guys are going to feel like that's a little bit too much, right? Like it's a vector, it's a force, it should exist in 2 or 3 space. And we're going to say, think 4 or 5. And the fact of the matter is that it doesn't even really get useful until you get to about 30. You guys with me on that? But we got to start somewhere. So we're going to start with physics, then we're going to lift a little bit from physics, and we're probably not going to make it all the way to machine learning. We're going to talk a little bit about how those things can work, but we're not going to get quite all the way there because this isn't a 4-year course in data science. You guys good with that? But this is where that ends. Okay, so I've got my 2D vectors, I've got my 3D vectors. I want to go back and talk about addition for a second. I digressed, well, really a long list. So these vectors must be the same dimension. And actually the output will also be that same dimension. Good on that? So this is going to be an operation, right? Addition takes things from Rn as a vector space and Rn as a vector space, really maps things like this to things like this. You guys with me on that? Okay, we're going to talk a lot about maps in here. So you're going to see me using this notation a fair bit, right? So this is addition is a thing. It maps space like this to space like this. How about scalar multiplication? How does that work? Oh, I'm sorry. Do you guys want an example of vector addition first? Probably. Let's do it. Here's the vector 1, 2. Oops. Let's add that to the vector 3, 4. Now, I know you all probably want to be very creative here. Don't be. How would you define this? Don't worry. Don't worry, John. I'll get to your questions.
4, 6.
Good. Perfect. Okay. So to answer John's question of, so what is the definition of a vector in linear algebra? A vector in linear algebra in this context is going to be a, define this. So a vector in this class thus far is any member of R n, thought of as a vector space. And what that means essentially is that it's a point in Rn space that you put square brackets around instead of point parentheses. And then the tools that we're going to have to manipulate it are going to be vector addition and scalar multiplication. A little bit later here, we'll get to defining more general vector spaces. And then a vector will be any member of a vector space. But for right now, all the vector spaces we're thinking about are Rn's. And so that's what it is. Is that clear as mud? Okay. So let's talk scalar multiplication for a second. Okay, so first I'm probably going to have to define a scalar. Anybody who's had a little vector before? What is a scalar?
It's like a constant.
Yeah, it's a constant, it's a number, it's any member of the real numbers. Is with me on that? Okay, we are occasionally, towards the end of the course, going to talk about complex numbers, in which case the scalars will be, or sorry, complex vectors, in which case scalars will be complex numbers. That makes sense? When we get to the vector space section, I'm going to talk a little bit more about how that expansion works. But for right now, I want you to be in vectors are made out of Rn's in a little column, and scalars are just members of R, right? They're numbers. No, it does not have to be an integer. Any member of R works. My examples, they're going to tend to be integer. And in fact, the vast majority of lectures you see, they'll tend to be integer. In actual data, they are usually floats, so some decimal garbage. Technically, they're allowed to be any member of R for any of the coordinates or for the scale. You good with that? Does everybody understand what I mean when I'm saying coordinates of a vector? Yeah, on board? Okay, cool. All right, so let's talk scalar multiplication. Let's talk through this by example. If you wanted to take 3 times the vector 1, 2, what would a 5-year-old believe this to mean? Okay, fine. You can upgrade them to when's 2nd grade? 8? Is that more or less right? I don't know. I don't know anything about children. At some time around 8 years old, we teach kids to multiply, right? How do we teach them to multiply? Other than telling them to memorize the multiplication table.
You count groupings of those numbers and add them together?
Yeah, you just do repeated addition, right? So 3 times 5 would be 5 plus 5 plus 5. Okay, so I'm going to do that same thing for vectors. Really, I'm going to define the scalar multiple of 3 times 1, 2 to be 1, 2 plus 1, 2 plus 1, 2. What do you get out of that?
Three, 6.
Good, you get 3, 6, which just so happens to be 3 times 1 and 3 times 2, stuck in a little box together. You guys all see that? So you can think about this as 3 times 1, 2 is that little 3 needs to be distributed into those spots. And so we get 3 times 1 and 3 times 2. Everybody with me on that? Okay, cool. Okay, guys. So scalar multiplication itself then is a map, right? So if I have AV, Right, this is how I'm going to write it. I'm going to write a letter A and a vector V next to each other. And that's going to be multiplication, which is a map from what kind of thing? So what are the two components of that? What's A?
All real numbers.
Yeah, A is a scalar. It lives in the real numbers. And V is a vector, right? So as a vector, it lives in some Rn space. And then where's the result live?
In some vector of Rn.
Yeah, it is some new vector of Rn, possibly the same vector. You guys with me on that? When would it be the same vector?
If A is 1.
Yep, if the scalar is 1. Is there a special vector I should talk about someplace in here?
The
0
zero
vector.
Yeah. So if you've had a little vector analysis before, or if you've had conversations about vectors before, you know that there's one vector that's very important. So the 0 vector. It's the vector filled with zeros, right? And it's denoted 0 with a vector hat over the top of it. You guys all with me on that? Okay. Why is the 0 vector important?
Shouldn't it be true for every case that we analyze or something like that?
Yeah, basically the 0 vector is like 0 in the real numbers. It's kind of a pain in the ass, and you should think about it every time you do anything. That sort of makes sense? So normally I appoint someone to be the keeper of the 0 vector. Alexis, how do you feel about being the keeper of the 0 vector?
Sure.
Okay, so your responsibility from here on out is anytime I make a statement about anything at all, your job is to ask, but what about the 0 vector?
All right.
And I'm just kidding, don't make that statement. Not every time. But anytime I haven't considered it explicitly, ask. And usually I should appoint a backup 0 vector keeper. Anybody else want to be the backup 0 vector keeper? Okay, sorry, Jordan. All right, so any questions about the ideas of vectors at all? Okay, cool. I'm going to need just a couple more thoughts about vectors before we move on to dot products and lengths. And those are going to be linear algebra only thoughts. So these should be new to people who have seen vectors before. So a linear combination of vectors v and w is a new vector. Probably think about the word new there. Of the form. Okay, so this is our first use of the word linear in the class linear algebra. So this will be a point we want to pay attention to. Pretty good with that? Okay, so a linear combination is going to be a scalar multiple of A plus a scalar multiple of V plus a possibly different scalar multiple of W. You guys see that? So this involves two scalar multiplications and a vector addition. You guys with me on this? Okay. So here's a very sort of silly example that I feel like I should do. And this is kind of the style of question that I expect you to be answering in this course. So maybe not why. What category does a linear combination of V and W, both members of Rn, belong to? Okay, so category is a word that that I like to use, that I don't know if you've heard in other math classes. People who have had classes from me, I think, are bored of the word category. Category means basically, what kind of beast is this? Right? Like, is it a number or a chair or a matrix or a function of two variables or a cross product or, I don't know, a ceiling fan, whatever. You guys all with me on that?
It would be a vector in Rn, right?
Good. Yeah, I think this is a vector of Rn, right? So my explanation for this, it's a vector in Rn as a vector space. Now, that is not strictly speaking an explanation. You guys see that? This is what I would call the answer to this question. In a like layperson's context. Now, the answer that I want you all to use in linear algebra is statement followed by a y. So the statement is it's a vector in Rn. Or a claim, right? So you're claiming this. Now convince your fellows that this is the case. Not me. I believe that this is the case because reasons. But why would Shane believe that this is the case?
Because both the original vectors are in Rn and nothing's changing that.
Okay, yeah. So the explanation that I would like is something along the lines of V and W are in Rn. So AV and BW are in Rn. And maybe a since, if that's not obvious. In this case, I feel like that's pretty obvious, right? Because I just talked about it. But in the case that that's a piece of information out of a different section in the textbook, or a piece of information that you remember from calculus class, that might take some justification. Does that make sense? In this case, you might say something like, if you really felt like explaining this, which might be good practice here, since scalar multiplication preserves dimension. You all with me on that? Okay. So have I now demonstrated that this is the case?
Can you prove to somebody though that scalar multiplication preserves dimension?
Yeah, that's a good thing, right? I may not, like, I'm relying on a fact, right? if I'm relying on a fact, I really should go find that fact in the book and cite it, right? So this comes from the definition of scalar multiplication, which is on page 2. You guys with me on that? And then anyone reading this can go back and refer to page 2 and notice that it says that dimension is preserved on page 2. You guys see that? It doesn't explicitly say that, Jordan. Stop looking. But ideally you would go find the spot that this is explicitly stated and cite that spot. You guys see that? You can cite things by page number. You can cite things by theorem number. You might say that this is a fact from section 1, really 1.1. You guys all kind of okay with that? My question is, am I done with this problem? Have I fully explained why it's a vector in Rn? And this is the part where you learn to think friggin' critically. Be skeptical. Don't believe.
I think I would take it a step further and also say that vector addition preserves dimension.
Good. Yep, so this is like item 1, right? Item 2, AV plus BW is in Rn because AV and BW are and. You guys might notice that my punctuation on these is for shit because I keep thinking up new clauses, which is why my punctuation is for shit in general. Really, proofwriting should take 2 stages. So this is the kind of first stage where I'm skeletoning out the proof, and then I would go back and prose this out a little bit. You guys all with me on that? So because AV and BW are and vector addition preserves dimension. Page 2. Crap. They don't talk about it in a minute. It's somewhere else. You guys okay with this? Does this thought process make sense? Okay. Some of the questions in the book are about calculating. In that case, I don't expect a huge long-winded explanation, but if you, some explanation would be good. It's cool with that? All right. Any more questions about this as a thought? Linear combinations? Okay, cool. Last thought is, what does a set of linear combinations make? So if I have 2 vectors and I think of all the possible linear combinations of 2 vectors, what is that possibly going to make? Oops. So, in other words, if I say A12 plus B34, what category of thing is the set of all of these? Sorry, John, I missed a nope. What was nope about? Did I miss a thing that you were confused on? Oh, that was, did you have any further questions, wasn't it? Okay. KJ, kinda. That's really a good insight. Do me a solid and wait till the, let's see, we're not going to get to that today. Wait till section 1.3 for that. But yeah, matrix, sort of. Let's think geometrically. So
We are two.
Oh, why?
Because you have 2 dimensions in your vectors.
Okay. Would it always have to be R2?
Not if you had more dimensions.
Okay.
But in this specific case, because our vectors only have 2 dimensions, it can only be R2.
Good. I know for sure that this thing is a subset of R2 as a vector space. You guys all with me on that? Now, without teasing too far ahead into our course here, because this is going to be a kind of a recurring topic, asking about linear combinations.
Quick question, is that a less than or equal to sign?
It is kind of. It is a set inclusion as opposed to the little element thing. So when I say V in R2, this is saying V is one thing in R2, right? When I use this symbol, I mean this stuff, possibly infinitely many things, are all in R2. That sort of makes sense? This is going to be one class, guys, where I'm going to occasionally slip a symbol that that you maybe have never seen in, just because that's how my brain works, because I was taught to think symbolically in a lot of these cases. So if I throw a symbol out, do exactly what Jordan just did. What the hell is that, dude? Like, I don't know what you mean by that. It's all good. Does everybody kind of know that these big curly braces mean a set? Is that a familiar term? Think about it like a collection of things. Okay. So I have this set. I know it lives in R2 for the same reason that I just discussed, that a linear combination has to be in the same dimension, right? Because scalar multiplication means that each of these, A times 1, 2 will be a 2-dimensional vector, and B times 3, 4 will be a 2-dimensional vector. Now, in this case, these happen to make all of R2. But that's because the vectors 1, 2, and 3, 4 were a little bit special. You guys with me on that? So let me think about a different set. So I'm going to make another grouping. I'm hoping I'm getting John's question in the same time here. So I'm making a group of vectors that are A12 plus B24. Actually, let me make that even easier. Let me say B times the 0. So this means all the vectors that are made out of picking an A and a B and plugging them in. That's what I mean by a set. So I know that this is a subset of R2. You guys see why? So this is all the linear combinations of the vector 1, 2 and the vector 0, 0. Okay. Now, what kind of vectors can I get out of this thing? What's B times 0, 0 going to be?
Still the 0 vector.
Good. That's going to be exactly the 0 vector. I'm going to add the 0 vector to another vector. What do I get when I add the 0 vector to another vector?
The other vector.
Yeah, just the other vector. The 0 vector doesn't do anything, right? You guys with me on that? You can see that from the definition that's up a little higher. So what that means is essentially that I can just go ahead and this bit doesn't matter, right? Cross that out. And so I'm only going to get scalar multiples of 1, 2 here. You guys see that? So what kind of thing is a scalar multiple of 1, 2?
Just a vector in R2?
Yeah, it's a vector in R2, and specifically, it's a vector that's what to 1, 2?
Parallel.
Yeah, good. This is a line in R2, right? It's all the vectors that are parallel to 1, 2. So that looks like this. Get with me on that? Whereas the other one looks like all of R2. You guys see this? So a linear combination of two vectors in R2 can be all of R2, or it can just be a line, or what else could it be? Is there another option? So I know this is a subset of R2, right? It's the linear combinations of the zero vector. It's got to be a subset of R2. What subset of R2 is it? See you later, Alexis.
Would it be a point?
Yeah, good. It is a point, and specifically, it is the zero vector. Right, which, if you've had Calc 3, you're used to dropping the vector hat off of things and say, oh, well, it's a vector on one hand, on the other hand, it's a point. In this class, everything's going to be a vector, so I'm going to just go ahead and say it's a vector, even though it's really a point. It's good with that? So these three things are the zero-dimensional subsets of R2, the one-dimensional subset of R2, and the two-dimensional subset of R2. You can see that? We're going to talk about dimensionality quite a bit in here, but I just want to tease it a little bit at the beginning because it's kind of freaking cool. All right. Any other questions about kind of vectors generally? Okay. All right. So let's try.